Can you all hear me? Hello? Can you guys hear me?
Yes, ma'am.
Okay, great. So, before starting, what I wanted to know was do you guys have any doubts? Do you guys want to discuss something before starting? Anything related to your projects or anything else? Nope. All right. Apart from that, another thing, you guys, again, tomorrow's gonna be our last session together. Tomorrow's gonna be your last class, and then we would be wrapped up with the internship and training. So, if you guys, like, some of you might have, a few skills, or you might want to, take up some roles later on, want to extend your work and work as in maybe an HR or even like as a trainer of a certain domain that you think that you're good in. If you think that is a situation, you can text me and let me know, and then I'll forward a word. All right, so think about it. If you want to be like still be a part of this whole process, and that would be actually good. You will be getting certificates for that separately as well. So if anybody is interested, you can text me. And my internet is a bit wonky today. So if like somehow my voice cut off or anything, just let me know that you guys cannot hear me or whatever. All right. So as Lokesh sir was talking about yesterday, today we're going to talk about trees. And trees is like a type of data structure. What data structures are? See, they are an important part of programming. Why? It's for interview and stuff, but they're also like important. You should know data structures and algorithms well. That's what it is about. It is used to organize data. More efficiently your data structure are, the better your program will be. The better you organize your data, different type of data structures are used to, store the data and organize the data in different ways. So tree is one of those type of data structure which is used to store data. And the more efficiently you store data, the more efficiently you can fetch your data back, and the more efficient your overall code will be, like the speed and all those you can, you know take care of that. So first of all, what is a tree? Data structure is to organize. We can use algorithms to manipulate, and that's all. So trees are non-linear data structures. These are not linear; they are hierarchical. All right. So they are not stored, like your linked lists or your stacks and queues, which were like linear. Their data will be stored linearly, like one after the another. Your uh, trees are non-linear. They are often used to represent hierarchical data. For real world example, it could be like a company's like CEO would be at the top, then you have a manager, and then there's employees. This is how like a tree looks. All right. So there's like a starting point, and then there are like it keeps on like a tree. Like you make a family tree. Like in younger classes, usually make family trees and all that. That's how it is. I hope you all can see the screen. Is the screen visible to you all?
Yes,
Yes,
ma'am.
ma'am.
Okay. Yeah, so it is like like a family tree, all right? You can see it like that. It is non-linear. It is not linear. So tree have different components. Tree have different type of components. Uh, Trees are collection of nodes, vertices, and they are linked with edges, pointers. So these are your nodes. You can like the CEO is one node, manager is another node, employee is another node, and they're connected through edges, which are also known as pointers, representing the hierarchical connection between the nodes. So these connectors define, the hierarchy, the topmost, and after that, and after that, and after that. All right. So that's how it works. Node can contain data of any type, but all the nodes must have the same data. Like in an array, you can have a lot of data in an array, but all of that will be of the same data type. Similarly, a node can have any look, any data, any amount of data, but all the data type should be same for all the nodes. Let's say the first node has an integer, so all the nodes should have integers in it. So what a different, there's a root. The root of a tree is a node that has no incoming link, that is no parent node. Think of it as the starting point, which is the CEO over here. This is the root node, or this is where the tree starts from. All right, there's no incoming link, there's nothing above it. This is the topmost node, and it is known as the root. After that, we have children. So children have incoming links from the node above, which is the parent node. If two nodes share the same parent, they are known as children. It is similar. You can completely compare it to your one of your family trees that you used to make in your younger classes in your notebook. So a children node will be like manager is a child to the CEO, employee is a child to manager. Now these three employees at the same level, they are child to this one manager. So they will be sibling nodes. All right, these two managers will be like sibling nodes because they're child to this one CEO, the root node, right? Then we have the parent. The parent node has an outgoing link connecting to more child nodes. So manager is a parent node to this employee, CEO is a parent node to this manager. All right. Now these employees are not parent node to anyone because they are the last children over there. There's no outgoing link from these. If they had an outgoing link, they would have been a parent as well, but they're not. Then we have the leaf. A leaf has a parent node but no outgoing link to a child node. So, like your employees, these are leaves of the tree. They have no other children. They are the last part of your tree. You could, in a way, say like they have a parent but they don't have any children. So they are known as leaves. Then there's subtree. It is a smaller tree held within a larger tree. The root of that tree can be any node from the bigger tree. Let's say this whole is one big tree. This whole is one big tree. Portion, just focus on this manager and three employees. Also be said manager as a root and employee as the children. So you can say like small tree inside a bigger tree. You can call this manager, employee, all this could be called as a like a subtree to this complete whole tree, right? If you can see it, okay, if you forget about all of this part, like everything behind this, then this is like this manager and these three employees is like another tree. Then we talk about depth. The depth of a node is a number of edges between that node and the root node. Think of this as how many steps there are between your node and the tree starting point. So depth is how many these links are there from, let's say you're counting the depth of this employee. So from employee to the root node, how many links do you have to cross? So there's two over here, right? So depth of employee would be two. A manager would be one. And for C it would be 0 because it is the root node itself. So depth of the tree is calculated as the number of these links present from the node whose depth you want to calculate and the root node. All right. And then this height. Height of a node to a leaf node. Think of this as how many steps there are between your node and the tree's endpoint. All right. So they've given the height and everything over here. See, the height is 3. In this is separate tree, right? Here you see of 8 if you want to calculate the height. So there's 1, 2, 3 to the root, and depth is also calculated similarly. So height is the longest path from the node to a leaf node. The longest path from a node to a leaf node is the height of the tree, and the path from the the node to the root is the depth of the tree. The degree of a node refers to the number of subtrees. How many subtrees it has is the degree of the node. Is it clear? This is more of a theoretical kind of part. Like for doing these kind of data structures, you first need to be done with the theory. You should know how they are in, theory, and after that you can go on. These actually trees themselves are a bit of a more complex or a more advanced topic for Java. So you can, like, what I'm going to do is I'm going to go over as much theory part I can today, and tomorrow we can see if we get a chance we can try implementing it in a way if possible. But I don't know if you would be able to grab, like, it should be, but it's not that complicated. But first you need to understand how, the whole thing works. So that's what we're going to focus on today. And if you really want to understand how trees do work, then do revise it once today, so tomorrow when we talk about it you can understand it well. So now it's, why do we use the trees? Why do we need it? Trees can be applied to many things. Like if you have you want to, store data in a hierarchical manner, like your files are stored in your system, right? You have your root file, and then you keep on putting slashes and their files inside files inside files. If you want to store some data in that kind of way, you can go for trees. And they were unique property of storing, manipulating, accessing data. Trees form some of the most basic organization of computers. We can use a tree for the following: for storage as hierarchy, for searching. If you, it's like searching a certain value in, like, trees is pretty like fast. They can search quickly. To perform inheritance, trees are used for inheritance, XML, parser, machine learning, DNS. These are like some separate examples. Indexing, there are certain B trees and B plus trees can be used for indexing a database, right? In networking, for finding the shortest path, like because there's already, you have these depth and height kind of things, so finding paths is easier. Then how do you make a tree? So first you have your node, and then they've given the data type, and they have the root. First you need to make the root node, right? Then you write new node and give it a name. Like this is the value they've given it, because it's string, so they've given a string. After that they make a separate node 1, which would be the other node. Like let's say this was your root node, so this would be your node 1, node 2. You can do it that way. So they have node 1, and they did root dot add child. Are you seeing what they did? They had a node. First, they created a root node saying node string root is equals to new node, and they're given this value root. Then they make child of this. Like everything is a child of the root node, right? So you have your node string node 1 is equal to root dot add child, new node, and then you add the node 1 over here, and that way you can keep on adding. Now you want to add a child to node 1, you can say node 2 is equals to root. Instead of root, you can write node 1 dot add child, so a child to this will be added. So now there's different type of trees. There are different types of trees. There are these n-ary trees, and they're balanced trees, binary trees, binary search trees. These AVL, these are like too complex. You can like skip over them later if you want. You can like go over them yourself once. These are the ones that I would be discussing. So now, and like your binary trees, you can have try like 3 times or 4 times if you want, so they're just called in general as n-ary trees. The node can have child nodes from 0 to n. For a binary tree, which is like 2, bi means 2, so every like node can have maximum 2 children from 0 to 2. Okay, if there's a tree which has like every node has like certain number of children, like here we have the maximum is 2. If let's say the maximum is 3, so you can have 3, like you can write something like this is 2 array, you can have something like 3 array tree, like that. So, and this is a binary tree, so every parent has maximum 2 children. No, none will have like more than that. All right. The balance factor of a node is the height difference. Like that. So a balanced tree, what is a balanced tree? Is a tree with almost all leaf nodes at the same level. All the leaf nodes are at the same level, right? There's not like if these were not present, let's say 6 or 7 were not present, so it would have not been a balanced tree. But because all of your leaf nodes are at the same level, so it is a binary tree. Oh, sorry, a balanced tree. So, and it is most commonly applied to subtrees, meaning that all subtrees must be balanced. If all of your subtrees are balanced, that means your complete tree is also balanced. um So that's the thing, like all of the leaf node, like nodes that have no further children are at the same level. They're at the same level. Then there's a complete binary tree. So what is a complete binary tree? When every level, excluding the last level, every level is filled and all nodes at the last level are as far left as they can be. See, what they're saying is, except this last level, everything should be filled. Except this last level, everything else should be completely filled. But in the last level, what is the condition? That the leftmost, everything should be to the left side. If the 6 is not there, it's fine. But it cannot be that the 6 is not present, but a number is present in this last empty place. Everything should be to the left. See, these are the leftmost nodes, right? These are the leftmost nodes, so they are filled. If this 4 would have been missing for some reason, this would have not been a complete binary tree. Because then this place is empty, this could have been more to the left. In the last level, everything should be to the left. There should be no empty nodes in between. And apart from the last level, everything else should be completely filled. I hope you're understanding, right? Are you guys listening? Are you guys understanding?
Yes, ma'am.
Yes, ma'am.
Okay. So then there's a full binary tree. A full binary tree, sometimes called a proper binary tree. Every node, excluding the leaves, has two children. So every node has two children except the leaf nodes. Okay. Every level must be filled and the nodes are as far left as possible. Look at this diagram. See, everything to the left is complete. There is nothing over here, that is fine. There's nothing over here, that is fine. But every, because this is now a leaf node, right? So it's fine, it doesn't have any children, but everything should be filled to the left. Like it could not have been a full binary tree if, let's say, this had only one child, or because every parent should have two children, every parent has two children over here, and everything is to the left. There's not like this is to the right and then this is left empty. Then there's a perfect binary tree, which is like completely filled, you can say. Both full and complete. It's full and it is complete. All interior nodes have two children. All leaves must have the same depth. Like all the leaves are at the last, they're at the same level. Everything has two children, those kind of situations. So that's a perfect binary tree, which is full and it is also complete. Then there are these binary search trees. So this is what like we would try and quote in tomorrow's lesson, because I want you all to once yourself go over trees so you have an idea. So binary search tree is a binary tree in which every node has a key and an associated value. So every node will have like a key and it will have a value. This allows for quick lookup and edit. So if you want to remove something or add something or anything, you can quickly do that. Hence, it has the name the binary search tree. It has strict condition based on its node value. Important to note that every binary search tree is a binary tree, but not every binary tree is a binary search tree. So a binary search tree is always a binary tree, but a binary tree is not always a binary search tree. All right. So what's the difference? Binary tree, the left subtree of a subtree must contain nodes have with fewer keys than a node's key, while the right will contain node's key with greater than the node's key. Take a look. See, there's a node X and there's node Y. So you have subtree 1, 2, and 3. So the left values will have keys smaller than the right values. So then the node, let's say that the value over here was 10, and then you have to put so over here in the left side you will have a value smaller than 10, so you can say 9, and on the right side it will always be greater than that, so there can be 11. So that's how it is supposed to be in a binary search tree. The left values, that's what it says. See, the left subtree of a subtree must contain nodes with fewer keys, that means a smaller value than the node, while the right will have greater values than the node. So if this is 10, then this can hold values from 0 till 9, and over here you can have values from 11 onwards. You cannot have a smaller value on the right side and a bigger value on the left. And same will happen over here. Let's say this is 9, so this can hold values from 0 till 8, and this can have values greater than 9. All right. And AVL trees and all that, we are not going to go into those. So I hope you got an idea of tree. I'll like right now share it for sure. Like, oh, you can like go over, look into trees, and especially in binary search tree. We'll try coding a binary, like I will look up a question that we can do for binary search tree, and then yeah, but before that, I want you to be clear with how trees work. Otherwise, it will be very confusing for you. Is it kind of clear? Like, did you guys understand how trees work and what it is? Do you
Yes,
guys
ma'am.
have any questions? Okay, so now here this is a video, so I think we can skip through it quickly. Let me know. Let's see if it works first. My internet is really not working today. A tree is a non-linear Can you hear it? Data structure which is used for storing the data,
Yes, ma'am.
and it is
Yes,
made up
ma'am.
of nodes and edges without any. Okay. So here you can see that we represent a tree through node and edges. So here you can see the nodes are connected to other nodes through edges. So friends, tree is basically a non-linear data structure without having any cycle. So you can see that nodes are connected to each other but they never form a cycle. So here if suppose 6 is pointing to 9, so therefore you can see that it will form a cycle. So therefore this representation is not a tree, because in a tree you will find nodes having edges to other nodes, but you will never find a cycle. And you can always think of a tree in the form of a hierarchical structure. And also you can see that each node in a tree can point to n number of nodes in a tree. So here you can see the node having data as 1 is pointing to the 3 nodes by data as 2, 9 and 3. So there can be n number of nodes in a tree which can be referred by any node. So usually a tree is a way of representing the hierarchical structure where the parent node is called as root. So whenever we represent a tree, usually the first node, which is the parent of all other nodes, is generally referred as root. And you can see that it has many levels of additional nodes. So friends, in the tree you can see that one is the parent of all the nodes below it, and it's generally referred by the root because this is the root of the tree, and whatever the edges are coming out from this root, it's pointing to the other nodes. And here you can see that this structure can go to many levels, and also a node who is not pointing to any other node is generally called as leaf. So here you can see that node 1 is a parent of 2, 9 and 3,
Node 2 is parent of 4 and 5, and node 4 has no childs, therefore this is called as leaf node. Similarly, 5 is a leaf node, 6 is a leaf node, 7 is a leaf node, 9 is a leaf node because they don't have any children. Moving ahead. So friends, what is a binary tree? So friends, a binary tree is a special kind of a tree where each node has 0, 1 or 2 children and not more than that. Can have 0 children, 1 children or at max 2 children. So here in the below diagram you can see as root is the parent of all the nodes. It's having 2 children with data 2 and 3. The node 2 which is parent to 4 and 5 has 2 children 4 and 5. And at the last you can see node 4 which is a leaf node has 0 children. So friends, similarly a node can have 1 children and the other children can point to null. So friends, a binary tree is basically represented by a tree node. So here you can see a tree node consists of 3 things. One is the data part which actually holds the data. As you can see the data is like 1, 2, 3, 6, 7, 4, 5. And it is a pointer to the left node and a pointer to the right node. So these pointers are basically of type tree node itself. So here you can see the node having data as 1 is a basically a tree node and whose left is pointing to the node 2 and whose right is pointing to the node 3. So therefore a binary tree having a tree node consists of only 3 things. One is the data part, one is the pointer to the left tree node and one is the pointer to the right tree node. So basically the way we represent a binary tree in the graphical form is something like this, that it contains the data which you can see here and 2 edges coming out of it. So here you can see this is the left edge and this is the right edge, and we represent this edge to the left and right pointers. Moving ahead. So as we discussed in our previous slide that a binary tree is basically represented internally through a tree node. So friends, the structure of tree node is something like it contains data, it contains pointer to the right tree node and a pointer to the left tree node in an actual tree. And below you can see the Java code for representing a tree node. So it contains the data, and here I have taken this data in the form of integer and which can be any generic type. And it contains a tree node left which actually points to the node which is just left to this particular node, and one tree node right which actually points to a tree node which is just right to it. And basically it has one constructor which takes in a data part. So whenever we initialize a tree node, we usually pass the data which we want to store into it. So usually when a node tree node is created, so data which we pass into the constructor is stored in the data variable, and left and right at the time of initialization usually points to null, and later on we make them refer to the other tree nodes. Moving ahead. So let's quickly see a demo how we can create a binary tree. So when we initialize a binary tree, the root is actually pointing to null, and this root is also a type of tree node. Now let's say we have created one tree node having data as 1 and whose left and right is both pointing to null, and which is referred by this temporary variable. So let's say we want to insert this temp into the binary tree. So what we do, we simply assign the value of temp to the root. So it looks something like this. So when we insert one tree node, usually root points to that particular node because this is the only node into the tree. Now let's say we create one more node having data as 2 and whose left and right both pointing to null, which is referred by this temporary node. And if we want to insert this node into the tree, we know that root is already pointing to the node having data as 1. So one thing we can do here is we can either point root left to this particular node or root right to this particular node. So either way we can do. So let's say we assign temporary node value to root left. So it would look something like this. So now here you can see this is a binary tree having 2 nodes where root is pointing to the node having data as 1 and whose left is pointing to a node having data as 2. And here you can also see that root right is pointing to null and left and right of root 2 is pointing to null. Now let's say we want to insert one more node having data as 3. Now here we can insert this node into a binary tree at 3 places. One is at the root's right, and other two places are nodes 2 left and right. So basically we can place this node 3 into these three places which is pointing to null. So let's say we insert it at roots right. So it would look something like this. So now here you can see root is having data as 1 and whose left and right both are pointing to a node having data as 2 and 3.
So I hope like this, from this animated thing, I think it's more clear about how the trees are constructed. You have like a root node and then you have those children, and those children can have more children's ahead. Right? So tomorrow what we're going to do is we're gonna work on a binary search tree. So you'll be seeing a binary tree as well as we will be searching in it. Apart from that, do you guys have any doubts? You guys want to ask something or anything regarding like? I hope you all are already working on your presentation and the project and the video. If you guys do not submit it on time, let me tell you, if like the time that you would be provided with and you have not submitted it on time, you might not receive your internship completion certificate even though you were part of all the classes and all that. All right, just being a part of a class like that's like they would need a proof of that you were working actually. All right, so if you do not do it, you might not receive a certification. So please, you all, like whoever's present over, you all do take classes regularly. Please complete your work on time. All right. Okay.
Okay, ma'am.
Okay, ma'am.
All right. All right. So if you guys have any questions, you can ask me or you can just start leaving. So because this was all for today, and we will be discussing the binary search tree tomorrow.